That's
Let me
coming
know,
up now.
Shikhar. Mm,
Yes,
okay.
it's visible now. So you can put it in PPT mode.
Visible, yeah.
All right. Yeah. So, as I was telling, the first 45 minutes, let's cover some ground, take some question answers for that, and then again continue in the second half in a similar manner. So just hold
Oh,
your questions.
yeah, yeah. So can we know a little bit of yourself, Ms. Narayan?
Sure, I will do that. Yeah, I my background is mainly electronics. Okay, um, so I've been in the semiconductor design field for roughly 18 years. So my main work is on chip design. So I've worked in the past with companies including Intel, Broadcom, um, and so I've worked in a lot of chips which are in the communication on the enterprise, but not much on the automotive side. But since the underlying signal processing, communications, the computing are very similar, what I've done, probably this has happened in the last, I would say, 2 years, that I've tried to leverage my electronics background into the automotive uh, market to understand how all these autonomous systems are evolving. It is a very interesting field because it comes together of so many different parts: the mechanical, the electronics, the computer science, and how do you create this machine that runs autonomously. Very interesting field. There's a lot of interplay, so that is something I do in my spare time. I keep reading about this. I keep updating my knowledge on this subject. And it helps that these sessions, I interact with other engineers, I get more questions, I figure out the details, and that's the way I kind of accumulate the knowledge over time, because there is no textbook today to go and look for this. So this is all work in progress. There is a lot of information in various journals and technical articles. But I thought it's an interesting way to put it all and for people to have it as a starting point and then build their interest with independent study and research. So I hope that way this helps you all to get that initial insight or that initial spark, and then you can build on it and do something really wonderful. So first, I would like to say that we are living in very interesting times. You keep hearing this smart and intelligent for anything and everything. You can even hear it for a toothbrush. Whether it's true or not, it's a marketing gimmick. There is definitely a lot of interest and a lot of technical breakthroughs that are happening to create what is called this intelligent ecosystem. What is this basically? I mean, earlier, if you were to either do any computing, which is maybe by a desktop or a laptop or even a supercomputer, storage, memories, or communication, cell phones, for example, all the three, even if you took 20 years ago or 30 years ago, were nowhere in the radar. In about 30 years' time, we have made these devices so compact, yet so powerful, and yet so cheap that it enables more and more applications today. You can very easily see the kind of devices that are proliferating in the market, uh, including everyone having a smartphone, the kind of TVs available, the electronic gadgets, things that help you improve the quality of life. So all this is because communication, storage, and computing have become cheaper and cheaper. Not only that, more and more effective. So this intelligent ecosystem, whether the simplest example of either a retail or in healthcare, or if you look at automotive or any industry, the idea earlier was that as you operated, you generated a lot of data. But that data, there was not enough resources to go and compute and extract any useful information. Very simple. If you go to a mall and buy today, the first thing they ask you is your phone number, and they know what you have bought, to what amount you have bought, how often did you visit. So they pretty much collect a lot of data, and they are also able to process it. They are not just sitting on tons of data. They're able to process it, extract some meaningful heuristics or information about you or about a society or about even a state or a certain district, and use that data to do very targeted advertising. You would always get SMS messages or whatever it is, WhatsApp or any other form of communication, saying that, hey, there is this deal. Hey, this is available for a 50% discount. So this is all very interesting, very simple example, but an interesting way in which data collected has been what we call mined, the data mining, extract information or patterns, and then use it to again improve either the purchasing experience or get a better uh, customer to come in and again and purchase it. So that is a very simple example of data collection, what we call as the subject of data mining, and that is all your big data, what they say today. And how you process this data, there is a lot of traditional architectures, as well as this new age, whatever neural network and deep learning that is available for you to process and extract information. You can apply the same concept of this intelligent ecosystem for our autonomous vehicles. So if you have a car which has lot of sensors in it, you would have seen these examples yesterday, a radar, a lidar, a camera, a GPS. So all these sensors help to collect the real world data and then convert it into a digital form so that you can, what is called machine learning, extract information through computing resources so that you are able to function better. So this machine learning as a field has existed for more than 50 years. There are a lot of traditional algorithms which are used extensively. A big and hot field that is coming within that machine learning is what we call deep learning. Deep learning use what are called as neural networks. So these are networks connected to each other over multiple what we call layers, and they pass on any input information or data with certain attached weights to the next stage. This gets progressively done over multiple stages, and then when you see at an output, there is a certain filtration. This is very similar to what you can say like your petrol refinery, right? Petrochemical refinery. You get a certain crude of a certain mix, and when you go through the entire refinery process, you get certain outputs in different proportions. You can think of the neural network also very similar to your petrochemical refinery. Only that the neural networks are also trained to do certain tasks such as speech recognition, text, image, video, whatever. But a neural network needs to be trained. We will see how this training happens, and then when they do the deployment, how they infer in the real world and how successful or unsuccessful that neural network is. We will dive into a little basics of the neural network and how they operate, especially in the context of image recognition and classification. So what you hear extensively today, machine learning and deep learning, are all algorithmic techniques to extract useful information from a data which has been digitized through a certain sensors. So the machine learning and deep learning are only a subset of what we call as the artificial intelligence. An artificial intelligence network is more above and beyond a lot of just what we do in simple terms. For example, your phone, if you take a camera picture, it can recognize your face, the contour, and then it can put some funny stickers or intelligent. They can even recognize a person, like in a Facebook photo, etc. So that is all, again, deep learning at play, because over time you've recognized the space over and over, and that information has been encoded in the electronic neural networks. An interesting offshoot of all this work in machine learning is that you can get into the augmented reality. The augmented reality is, for example, a simple example is cars. If you are driving, when a human is driving, the machine or the intelligent system can recognize the roads and then overlay on your screen the kind of either the traffic you expect or how the road is going to be, what is the road condition, so that all you take you get the information up ahead. So that's a very simple example of an augmented reality, that the machine part of it recognizes the road, recognizes through its GPS its location, and then on your windscreen create a projection saying how this road is going to look going forward, even if when you don't have any visibility up front. It works the other way also. When the human is driving, the machine learns how the human is traversing a certain section, and that information also can be learned and incorporated in a neural network. That is a class of machine learning called imitation learning. We will also see an example of this much later. So the outcome of all this processing of collecting the data, digitizing, analyzing it, is that you can come up with a set of outputs or commands to operate or excite the drive-by-wire systems. When you are able to issue these commands, the car steers in the way that the steering or brake or acceleration unit has been commanded. Now you are in a new position as compared to the previous frame. Again, you can go collect all this data, both of the car itself and its surroundings. You feed the information back into this machine learning or deep learning system, generate the desired output you want. So if you're driving to a certain location and you want to reach in a certain time or in a certain efficient manner, you do the path planning, and that command is now again issued to the drive-by-wire system. And this loop continues in a manner such that certain criteria is always guaranteed: safety, fuel economy, efficiency of the ride, comfort of the ride. You can overlay a lot of factors in it, and accordingly the system will manage those commands. But the nice thing is this can then be a fully autonomous loop, and this loop is then becomes an intelligent ecosystem, and then that enables you the autonomous navigation of this vehicle. You can also overlay other things on top. Not only is your car able to perceive and control its action, it can also exchange data with other cars or to the infrastructure in terms of road markings or traffic lights or signboards, anything. That is the whole field of IoT there, Internet of Things. If each of these were also intelligent and they are giving back information, the car can also take that information and process it and do a much more better and efficient maneuvering. That becomes the realm of connected cars. So autonomous is one layer, and then there is also connected cars. The autonomous and connected cars together as a complete system, if it is a traffic management system, the whole thing, you can call it like a swarm. They can work and cooperate with each other to be very efficient overall, not just for your own vehicle, for the entire fleet of vehicles that are operating. Is this does this convey the overall picture? I can take a few questions here if you.
Narayan, actually, this connected vehicle technology you're talking about.
Yeah.
So there are a lot of other standards that are emerging up. So one of this is 5G technology. So this, do you think that it's going to really help this, or this is a question we'll part for some other time?
Now, what we see is that if every car tries to do its own thing, where is the cooperation coming? Because finally they're all going to go on the same infrastructure, which is the network of roads, right? How can these cars, let's say each of this is autonomous, but how can they cooperate together to make the whole system more efficient? That if you put the problem statement like this, then you can say that, okay, what is the data that needs to be shared? And what kind of a communication network is needed to share this? And what are the rules by which you play? So that will need the cooperation between maybe different car vendors, or there could be a safety regulation body which is enforcing and as the oversight for the whole thing. The thing is, finally, you have to play by some rules, right? It cannot be each for themselves.
My question was that this 5G is going to get into this technology, or there is another 802.11 standard?
Yeah, there is. I have seen another variant of the 802. I know certain companies have been pushing it.
Yeah.
There is, I think, a company called uBlocks or something. It's a Swiss company. They're trying to do that V2X using the 802 extension. Which technology wins? At this point, I don't have a bet. At some point, they will definitely standardize. So it all depends who's backing the standard and what kind of marketing and money power they have. End of the day. So it might not be the best technology that always wins. It is also what gets pushed by the OEMs or even a country's regulatory body. That's the way I see it. But irrespective of what will be that communication technology, we need to agree on what is the data that we can share meaningfully and be cooperating to coexist in that infrastructure. If you agree to that, then the other thing is, okay, what is the best communication?
Okay, thank you.
Yeah. Any other questions? Okay, so if not, I think this I thought was forms the framework to explain the intelligent ecosystem. And an intelligent ecosystem in the automobile world is the autonomous navigation. With the connected layer, it becomes more efficient. So that's the message I would like to convey here at the start. So everybody knows that the cluster of electronics or electronic units in the car today, they are only increasing. People want either for comfort or for user experience or for their safety, a lot of discrete electronic units in today's car. That becomes a very big market sell. Two areas that are seeing the biggest disruption. One is the electric powertrain. It can be whatever, battery or battery plus a fuel line. It can be a mix. The other is this assisted and autonomous navigation. So I see these two are the biggest. A third we can also say is the connected cars. Between them, the amount of electronic control systems in the car is only going to go up exponentially. And in the future, we're looking at something of a concept car here. This is a rendering from Audi. It's a car called AICon. It is a, I think Shekhar would have explained here, it's a level 5 autonomous and electric car, and fully automated. If you go sit and you can Google this picture up, there are very nice videos of this also, the demo car. There is nothing like a dashboard, nothing like a steering column, nothing like a brake acceleration or any other unit. You go and sit in the car as a passenger, not as a driver. And the car takes care of the navigation completely by itself. So this, you can say that this is a computer, a high performance computer sitting on 4 wheels. That's the kind of electronics and control systems and software which is probably going to figure in the car in the future to enable the autonomous navigation. So I think people would have heard of this case, right? So connected, autonomous, shared, and electric, the 4 pillars in which we are looking at the future of automobiles. Some of this again is a rehash of what Shekhar would have told you yesterday. It's more for an overview and the introduction leading up to the main part of the talk. Radar is always there. You could have a long range, medium range, short range, and you could have it in front of the car, on the sides, on the rear. And each of this will perform many of the autonomous or assisted navigation functions. It could be a cruise control. It could be lane departure or lane keeping services, cross traffic alert, parking assist, whatever. So the radar figures in multiple places in the car. So a lot of vendors, including Bosch, Continental, they are working on all this. There's even radar facing inwards, looking at the driver to be able to sense whether he's alert. Does he have his hands on the steering? Is he paying attention or is he distracted? Is he watching a screen, mobile screen, eating, drinking, dozing off, whatever? A lot of interesting applications for the radar. Radar is very useful because it's all weather, all light condition. It is very operational. Only thing is the collected data from a radar is very sparse. So to make a full rendering or a virtual remapping of the real world is not very effective just with radar. But people are working on it to look at what is called an imaging radar. So you use these RF signals to collect data, but you collect data that looks almost like an image, like a pixel. And you should be able to make the full what is called a recognition of the object just with the radar data that you get back. So that's one line, radar. And of course, you would have seen LiDAR. So LiDAR is very close to our visible spectrum. It projects infrared light onto a certain field of view, collects back the light reflected out of various surfaces, and then you can use that information, which is similar to how you take a picture with a camera in visible light. That can serve as the image for doing all your recognition and classification. So the data that you get is much more richer than radar, but not as good as your camera systems. The LiDAR still will suffer because of fog conditions, etc. But at least you own the projection system. So you don't have to rely on sunlight or any other artificial light to illuminate the scene. But it's still not all weather. So the camera among the different sensors is the one that is the highest pixel in terms of the richness of the image. It is the best. It is also one of the cheapest. And a consumer grade camera versus an automotive camera, there is just vast differences. You take a picture, you don't like it on a camera, you can delete and throw and get a new picture. That doesn't work with the automotive cameras. They need to have extremely good dynamic range, extremely good contrast of images, and very adaptive. And they should be able to work in very rigorous environments of temperature. So a lot of it is, very tough ask for the automotive camera. And that is what gives you a lot of this image data for you to recognize and classify. There is also the ultrasonic sensors. It is already figuring in the rear bumpers for you to do a parking assist. You will see later an example in a Tesla car where they use these ultrasonic sensors to detect the immediate vicinity around the four corners and be able to see whether an object is present or not. So all these four main sensors let you assess and find out what is in your surroundings. And each of these sensors has their own advantages and disadvantages. So one sensor alone is not going to win the day for you. This is like our human sensory network. Yes, the eye is the most powerful, but there are certain scenarios where the eye cannot function. If you go into a dark room, your eye is rendered useless. So immediately what happens, you become alert to the other sensors. Your sense of smell, your sense of hearing, or even your sense of touch gets heightened. So that's something very similar, that the kind of sensors that you put, you should be able to rely on one sensor over the other based on the environment conditions. And together, they will form that system which is most efficient, and then you can look at the trade-offs between them. So these four collect data around the vehicle. You also have your own vehicle data, because these are all now relative positions, right? A radar, a LiDAR will tell you what are the objects around you, how far they are, the range, what direction they are moving, what relative velocity they are moving, what is the angle to them, all that details. But this is all relative to your car. How is your car moving or traversing? So that comes from GPS or your inertial measurement units, your gyroscope, accelerometers, which are very common in cars for their traction control, etc. And then you also have your steering angle sensors, the wheel speed sensors. These four, the simplest examples, will collect data of your own vehicle. And between them, we now create that virtualization, or whatever is the real world scene. We create that electronic rendering of the scene. Once you are aware of all the different players in the scene, it is for you to now calculate what is the next step you have to do. So where are all these objects going to be in the next few time instances? Where is my car going to be? Is there a possibility of collision? Do I have the space to maneuver? If not, what should I do? If yes, can I accelerate? If no, should I brake? Should I steer? So those are the end results of the computations that you will do. To start with, you collect the data. Second, you identify the scene objects. Third, you compute their positions in the next few instances. Once you compute that, you have something called the free space estimation. In that free space estimation, you calculate what is the necessary levels of control that you want for your steering, acceleration, brake. Give that command to the sensor units, the drive-by-wire units, and then wait for the next frame to recollect the data. So on a frame-by-frame basis, you do this over and over again and have a, have a control navigation of the autonomous system. Like I said before, whatever data you collect, this is a LiDAR 3D point cloud. The idea for you is to generate, this is a color-coded map just for rendering. The color indicates the depth or the range to certain objects. And then once you know where are the different objects at what range, you also recognize them and put these 3D bounding boxes to say that these are objects, and then classify them whether it's a car or a two-wheeler or a traffic light or a signboard. So that classification is where again the neural networks come into play, and we will see how these convolution neural networks extensively used for image processing will be utilized. This is a very simple example I want to say. On the Tesla car, what are the different sensors? We have a front-facing radar. There are about 8 cameras in all. The mirror is actually a camera on the side view. And there's 3 cameras in the front windscreen itself, right behind the rear view mirror. These have different focal lengths, so long range, medium range, short range, and with different field of view. And what you see in green are the different electronic ultrasonic sensors, 3 each in the corner. So within a few feet, let's say up to 10 feet, you can use this to detect objects, very useful for your lane keeping and lane departure warning systems. And the last is your GPS, which is going to collect the data for you relative or in the absolute frame in terms of your coordinates. All of this sensor data comes into a central processing unit. Tesla calls it the FSD, full self-driving hardware. In that is where all the computations necessary to do the path planning takes place, and the necessary directions to the drive-by-wire systems are issued. Like I said, each sensor has their own advantages and disadvantages. The idea is to have them all cooperate or put together, get the best of all the worlds. So this is why we need sensor fusion, because each of them works or doesn't work in certain scenarios. How do we make sure that we are able to aggregate the different sensor data and be able to operate reliably in all conditions, whether it's light or whether in extreme weather conditions or whatever? This is a very simple example of a real life scenario where in the absence of a sensor fusion, things went wrong. This goes back to almost 5-6 years ago. A Tesla car on a freeway was running in the autonomous mode, and you had a truck which was making a left into the side alley. And as the truck was crossing the road, the car did not recognize the truck, and it hit the truck, and the driver got killed. The main reason was the camera. It had a camera, like what we said before. The camera was not able to detect this white on white. The sky, the background was white. The truck, the side was white. And there were very few features to distinguish in a camera image. And the other thing was that it was going laterally. It was not either coming towards you or away from you. It was going left to right. So there was no way for it to recognize this, or it was looking as though it was some billboard in the distance. So that was a problem with camera. The radar is also failed in this case because it didn't have much of the elevation information. A lot of data was collected just below this truck's heightened level, such that it completely missed this. So because both the sensors were not able to do a reliable detection, they failed. The fix was that one, to change from a very monochrome camera to a full color thing. And second also is that on the radar, have the elevation information to some extent, a couple of degrees. I think that's where again the imaging radar comes. We just don't need a few degrees. We could have a couple of degrees of information so that we get the complete picture of an object, not just few sparse data points. So this sensor fusion is definitely important to help us get a better, more complete and a more reliable detection. Without a proper detection, if you miss the players in a scene, you are not going to have the correct computations, and you are going to have some erroneous results. So that is where a lot of work needs to happen. The other thing is, even in the sensors, we will have various sensors, but how do we want these sensors to work together? A radar, a camera, a lidar, could each of them, based on the image that they capture, make sense of their own scene and then give their own decisions? For example, in this case, just for illustrative purpose, a camera says that, hey, there is a kid on the road and it's playing with a ball. The radar says there is no such object. Then who will you believe, right? The camera insists there is a person. The radar says no, there is none. Who will you give weightage to? And because each of them recognized and came with the decisions, there was no way in which to make a proper call. In the end, this was actually a way to spoof the camera sensors, because this is actually a painting on the road with the necessary elevation to make it look like a child playing with a ball. In reality, it's a drawing on the road. So that fooled the camera. The radar was able to do that. But again, you could always find a scenario where the camera is correct and the radar is wrong. So how you want to do a decision between different sensors, the idea is that each of the sensors give the raw images or the raw pixel data to a main perception engine. So it is a centralized decision making, not a distributed where each of the sensors recognize the objects by themselves. In their limited in their limitations, they could do a wrong detection, and it is very difficult to correct for it. So this is also one important thing, to have a centralized architecture for sensor fusion and decision making. So you could have the radar and the lidar together collect the points, overlay into a set of whatever trace points or 3D point cloud, have the camera capture the same scene, get the RGB data. So there is now RGB, the three primary colors, with the depth that becomes one composite image or a set of vectors for the neural network to process and identify and classify the objects. So when you do that, you have picked the best of the both worlds in terms of what is very good for depth. And you have also picked the best of the world in terms of getting the richness or the details of the objects. So this is a very interesting way to again fuse the sensor data and have that composite information for you to process. The last one in this, when you collect sensor information and when you're doing the fusion, is that, like I showed in the previous example for the Tesla car, there are a lot of sensors mounted in different locations of the car. How do you merge or bring the spatial alignment? So that is about a very simple geometric transformation or of your coordinate frames. So I know this camera is in my front windscreen and this camera is 90 degrees to my left, looking at my left side. And this is a camera on my right side looking at cross traffic on the other. So each of this, you can bring it together into a common reference frame. And then you can get this complete 360-degree view of the surroundings in terms of spatial. The other thing is also in terms of time or temporal. Each of these systems is generating data at what we call as frame rates. So it can be whatever 15, 20, 25 frames per second. So 25 frames per second means every 40 milliseconds, you are getting a data. It could be an image, it could be a radar image or a lidar 3D point cloud, whatever it is. But these are not, these might come to a main or a centralized processing unit at different time stamps. So each of the data that the sensor sends you, they put a timestamp, and then it comes to the main processing system. They look at this timestamp and try to synchronize all these timestamps so that you are looking at that information at the same time instance for across all the sensors. So if you have something in between, you could do some interpolation or extrapolation techniques to make sure that you are actually looking at the exact instance from all the sensors. So both the spatial and the temporal alignment or adjustment is needed to get this composite view of the surroundings at every frame instance that you want. And when you have this, you reconstruct that real world map into a virtual image in your electronic processing system. It could be a CPU, a GPU, there are a lot of options there. And then there are these powerful estimation techniques. I think a few people would have heard of these Kalman filters that lets you compute what is the expected value or the expected outcome in the next few frames. It is computationally powerful, but with very low memory end. So it's a very powerful computing technique using Kalman filters. It's a very popular algorithm. So with the collection of the sensors, different sensors, because they have their own advantages and disadvantages, fuse the raw data, align them both spatial, and then reconstruct this virtual world, compute the world how it looks in the next few frames, is what is the starting point now for the next step, which is the path planning. Once you are able to do this, your next step is to now go and do the object detection and classification. So any questions till now? We can take a few questions here.
Narayan, actually, this is Ramdas here.
Yeah.
So actually, we were talking about the sensor fusion architecture actually in the previous slides. The kind of data that each sensor gives is different in its culture and its form. And then obviously then they have seen yesterday that the GPUs are deployed usually for processing this kind of data. Okay. Is there any kind of the pre-processing done on this kind of data to bring to the common reference?
It is required. I'm just giving a very simple example where it's like a coordinate geometry, right? Yeah. Each of this is located, let's say your rear wheel, this is your reference frame. With respect to this, if you're doing all your computations, you know that the coordinates of all the sensors where they are located with respect to this as your origin. So that is the simplest geometric transformation you will do. One. So it can be XYZ or it can be angular also, correction. Second is, in time when you get the data, if you're not synchronized, how can you do the synchronization, or how can you extract this intermediate data? A lot of work is there on that also, on that aspect also. The final thing is, when you create this, for example, when you see a scene and when you close your eyes and you render it in your memory, have you correctly taken all the geometric and all the time stamp information so that the picture you have, the mental map, is not distorted or wrong? Correct? It's like very similar to our human visualization. So the virtual rendering that you do, such a picture might not exist, but for computation, you create that. When you create that, you make sure that you have not distorted in time or in space.
Okay. So is there any method to handle the false positives and true negatives here?
Correct. There is where it all becomes the training data. One is the awareness of the sensor limitations. Okay. If you're relying on a camera sensor to operate in a fog, yes, that is a limitation in itself. Your data quality itself is poor. Let's say you worked around that. The second thing is, when you have the data, let's say from the radar itself, which works very well even in a fog, the thing is, how well did you train your object detection and classification network to the wide variety of different objects that you will see in a field or in a scene, right? Unless you have trained it very well and extensively, you are always going to miss out on certain detections. So it becomes the point I'm trying to tell is, it all depends on how good is your training data and your training sequence before it gets deployed in a real world and starts doing the inferencing process.
What is the popular hardware for this kind of processing and available in the market? I heard the NXP is doing a lot on this.
See, NVIDIA has got a lot of platforms. There is something called Xavier, and that's a very powerful way. The thing is, for image, or if you think of this as a composite image of either a combination of camera, radar, and LiDAR, the GPUs, the graphical processor units that you use either in your desktop or in your gaming, they are very good at processing this pixel by pixel information. And each pixel, let's say you have whatever 1 million, 2 million, 10 million pixels, can be independently processed from any of the other. So what they do is they put a lot of algorithmic processing units. Each of them is independent of the other, they can do a very heavy duty computation and get you what is the data that is for the next step. So the GPU works very well for the neural network also, because in all these things, you will see that when an image, a raw image, we will see an example in the next. When the raw image goes through the neural network stages and they get processed, you are refining the image to either heighten or lower certain features or characteristics. So when you go from layer to layer, it is a transformation of the image, and the transformation of the image is done very well through GPUs. So this graphical processing units come very naturally for all this neural network and image processing. So that's why NVIDIA's Xavier is a very good platform to go and try out the stuff.
Is it something like a commercially available off-the-shelf solution, or
Xavier is? I think Shekhar.
Yeah, he had shown yesterday, and there's one board.
Correct. You can buy it. You can buy it, and then you don't have to invest anything on the hardware.
But what is the trend in the market? Like the car makers, they have their own hardware solution always, or they take this commercially available options.
See here, what has happened is the car makers have been left behind, because a lot of this is coming from the IT or the chip industry, like NVIDIA and so on, right? So the car makers have no way to do these chips in-house. In fact, even the regular chip manufacturers of automotive, like Infineon, they are behind Qualcomm and NXPs and NVIDIAs of the world, right? So there is a shakeup that is happening because of the computing power which is required. Secondly, the software is no longer your embedded C software, which the automotive is used to, but it is very high-level algorithms working at a very high speed, which is again coming from like the gaming industry, the graphical processing industry. And there again, the current OEMs are left without options. They have to buy the software libraries and the software stacks. So again, here the OEM will largely end up playing the role of an integrator, and some level of application code will be done by them. So just like we saw yesterday, we can have the hardware, we can have some starting libraries, but then the decision making has to be implemented by us. The algorithms are available, but the logic has to be defined by the OEM themselves.
Okay, thank you.
Yeah, I think just to add to Shekhar's thing, so yeah, when a car OEM integrates these as discrete control units or black boxes, that becomes suboptimal over time, because a lot of it is an interplay of different subsystems, right? So just functioning on its own is no more going to serve it. How do we collectively pool this information to make a better sense of it is what is driving the autonomous navigation. Tesla, because it started from scratch, and since they own the complete system, it could be the mechanical, the electronic, or the computer software stack, they are able to do a better integration and deliver a higher quality of what we can say as the computational resources available for all these decisions. So I think it's for the OEMs also to disrupt, or for the module providers to start integrating more and more of it into a single system. I just showed you a picture, right? The FSD hardware or the board is one single system with duplicated processing and memory subsystems, which is handling pretty much all the computation and decision making. So when you have that kind of a centralized and integrated system, and with all the redundancies, it is a powerful way to compute and efficient also. Answers
Okay.
your question.
Yeah. Thank you very much.
Yeah. Any other questions here? Okay. So till now, what we have seen is the sensor, the different ways in which you will collect the data, their advantages, how the sensors information can be fused together at the raw data level, and you work on that composite data in your machine learning or deep learning systems to do the classification, the detection, classification, and tracking of the objects. That becomes the first criteria to do the path planning. So the neural networks, so this is a rendering or a visualization of our human neurons, which are really wonderful creation. So if you have read in your biology, there is all this stimulus. It is essentially in the human body an electrochemical process, and the firing of the neurons is what triggers the next one in the chain. With whatever excitation it goes, it triggers the next, and these become the relays going from, let's say, any of your sensors, which means your touch, smell, visual, hearing, goes to the brain, the central processing unit, and the brain then interprets that information and sends back or relays a set of stimulus for the neurons to act. So these could be your motor neurons, whether you are playing a game or you're running away from a certain situation or whatever action, or you're even driving. The brain now commands the motor neurons to do the necessary action. So it's a very wonderful, very complex, and very adaptive systems. A lot of this, we come up like a empty or a blank slate based on our experience and based on the kind of exposure we have had, the training we have had. We start forming these relay networks and have our preferences, our likes, our dislikes, our things that we are very good at, things that we are not probably that good at. So that is how you get the entire personality of a certain individual. So starting from a blank slate, it becomes how you are trained and exposed. The idea in the electronic world is to create a similar set of relay units. So you can think of each of these stages as a set of trigger points or neurons, and whatever is the connection going between one stage and the other is these dendrites that are the connections. So each dendrite will have a certain weight, or to a certain trigger, the amount of electrochemical, the chemical amount of chemical released will differ. And that has happened during your initial formative stages. Same way here for the electronic neural networks or perceptrons. If each of these are a relay stage, what goes in between are the different connections with different weightages. So the first level, if this is your eye and this has captured an image, to the next level or the next stage is a set of weights or importance that you add to each of this. Could be a pixel or to a certain feature or whatever. And as you progressively go down this, you add the necessary weightage at each stage, so that when you have the final result, it is about a certain thing that you either recognize or do not recognize. So the main point I'm saying is, in humans, the learning happens by forming these connections, making certain things stronger, and this is an electrochemical process. In the electronic neural networks, a very similar thing by the amount or the weightage that you add. How you add the weightage, we will see, is how you train the network. So the convolution of the different inputs or the different stages is what gives a certain end result. And like how as kids we learn by looking at real life scenarios, or you go to a school and you have a supervised learning, these neural networks will also need to train. In this case, the training is by saying what is the weightage that is associated with each of these connections. And then for you, like how the real life exposure or scenarios are your training data, we need to have a set of training data for the neural networks to be able to perceive. And the overall goal is to recognize these objects correctly and have a certain value of false negatives and false positives. That is, those are the scenarios where maybe an object didn't exist and you recognized, or alternatively an object is there but you are not trained for it to recognize it correctly. So it is a continuously evolving and learning process, like how we don't stop learning after school or college. The neural networks, yes, to start with, they will do supervised training, but over time, it is for these systems to go and recognize what is different from what they have trained, be able to do some intelligent heuristics and self-adapt. That's where the real artificial intelligence comes. Until that stage, you are pretty much like any other machine learning or a deep learning algorithm. The artificial intelligence comes when you see something that is not what you train for, but you are able to build on it and retrain your network or incorporate it so that next time you are able to recognize that correctly. So in the realm of autonomous vehicles, the thing we said is when we collect these different sensor data and fuse, it is like an image for which there is pixel information, and we have to look at patterns and extract objects out of it. This is like doing so this field of what we call as convolution neural networks for the image processing is like doing a word puzzle. Let's say you want to recognize these different words in this jumbled array of alphabets. Everybody has their own technique of solving this word puzzle. So for example, you will take the word sun and then you will scan it. You could go row by row. You could go column by column. You could go a leading diagonal. You could go a lagging diagonal. Over time, you will even start looking backwards. So each of this is one step of your algorithmic process to determine where are the potential locations of the word sun. And you will end up with this once you finish going through all these multiple steps. And you can now go and repeat the same thing and do for a different word. And over time, in this array, you pretty much recognize all the words that you want to do. A convolution neural network is very similar to solving this puzzle. So for the set of objects that I want to detect in the scene, I need to create this pattern. The word for it is a term filter. I have to go start running this term filter over this image array, look for these patterns. And when I see this pattern, I pass it to the next stage. And as I keep promoting it, and you start detecting more and more features from every stage or every layer, I get a complete image of what I want to detect. So that is the feature extraction in each level or each layer of the neural network. A very simple example here, let's say this picture here is rendered in black and white, okay? And I have, this is my tile or this is my pattern, like the sun or the moon. This is the pattern or the term filter. Think of it as saying that don't worry about this value. You are transitioning from a very dark to a very bright region. 0 is like grayscale. So if you just run this simple 3 by 3 pixel over this picture, which could be maybe 1 by 1 megapixel also, even by running something very simple, you can start to see a lot of the features that came from the original picture. For example, the height, the hair, the curvature here. A lot of things just come by a very simple term filter, which is very easy to construct and do the convolution. So this is the actual convolution. This value run over the entire pixel array. The ones that match to it, they will have the highest correlation and they will stand out. The ones that do not will stay in the background. You do the opposite instead of a vertical. If you do a horizontal filter or a term filter, where you check for a dark to a bright transition in the horizontal frame, again, very easily you can start seeing the contours of the eye, the lips, a lot of things. So the message here is that you can create a lot of these matrices or term filters to start extracting simple features, and you can keep overlaying this and adding and extracting more and more features. So for example, in a face, yes, I will start with this, and then next I will look for an oval or a spherical shape, and then between the two, can I look for an eye, can I look for a nose, can I look for a lip, and then can I look for a face, then for a body. So though this need not be as straightforward, I'm just giving an example of how you progressively start with very simple shapes or lines and start extracting to richer and richer features and objects. It is also how you draw, right? When you draw a picture, you start putting the lines, then the curvature, then the shapes, then the textures. You keep overlaying information in every stroke or every iteration. The neural network is also very similar.
Can you explain again how these numbers are mapped to the grayscale?
No, don't worry about the grayscale here. The idea is that when you get a pixel, right? Let's say just take a camera and you take a picture of a scene. Let's say there are 1 million pixels, right? 1,000 by 1,000, whatever array. Each of that pixel will have 3 primary colors. And each of these primary colors will be what is called a 8-bit representation. So they will have values from whatever 0 to 255. Or even minus 128 to plus 127. 0 being in the middle is your grayscale. I'm just giving you an example here. Minus 128 could be your darkest black, and plus 128 is your brightest white. You following me?
Yeah, I'm listening. Thank you. Yeah.
Okay. So now I don't care if it is minus 128 or plus 127. I will just divide the whole thing by 128. it is called normalization. So -1 is my darkest, +1 is my brightest. So in this case, the scale is going from +2 to -2. So what does -2 mean? It is the darkest region. +2 is the brightest. And then there is a gray transition region in between. This is done on a vertical orientation. So this first three, first column, these three entries say that I am transitioning from a region which is dark to a region which is bright on a vertical axis. Got it?
Yeah, got it. Yeah.
Similarly, this one's on the horizontal axis. Just by doing these two, you have pretty much extracted all the line features. First step, a very easy step. Then you can build a different term filter, which is maybe a leading diagonal, lagging diagonal, whatever. Start looking for a spherical, for a straight line. So the point I'm trying to make is you can keep complicating these term filters, accumulate the information from the previous decisions, and then in the subsequent steps, start recognizing the features, the eyes, nose, ears, the face, the body, and that's the way you complicate it, or the way you build it to a certain object. Makes sense?
Okay, yeah, thank you.
Yeah. So this is a simple illustration to say that if I have this tile, which is the pattern I'm looking for, and let's say for our understanding here, the three primary colors, I will run this tile over this entire pixel. When I do the scan, what comes out of that result here is the feature extraction for that stage, for that color. Got it? This is only first stage. So from the first stage to the next, you have extracted and reduced the space or the pixel array, but you have enriched certain features, like how we saw in the previous picture. The vertical and the horizontal lines of the pixel frame, we have extracted. Then you can have a different term filter or a pattern. In the next stage, you do a similar one, and then you collapse it into a smaller subset. But richer and richer, it gets richer and richer in features, but gets shrunk in size over multiple neural network stages. What you will end up with is like saying I have a deck of cards here, and in each deck of cards, I have extracted certain features for you. Now against this result, I want to look at and say what have I detected. So this is where a card that you got is matched with what it has been trained for. And when these two have very good correlation, you say, yes, I see a car, I see a face, I see a certain object. So that is how this convolution neural network happens. In this, there are two phases. One is the training phase, where you have to actually, like saying, I will give the question paper, I will also give the answer. So the question paper is your picture image. The answer is what is the object in that picture. With this question and answers given to you, you work back, in this case, what are the weights in the different stages of the neural network, so that when I do this, I get the correct answer for every question, and I am reliability detecting all the images. That entire fine-tuning process of putting the weight so that your answer matches the answer already given is the training part. Once you have done the training part, this is like writing a trial exam. The actual exam is when you get totally new images. You don't get the answer for the images. You come up with the answers now. Now, if in that actual test, which is called the inferencing, you didn't succeed. You got only 50%. That means 50% of the objects you missed. Then the training is not sufficient. They will say, okay, go back, study, and come and write this exam again. Then you have to again go through this entire training process, go study all over again, and then reappear for this exam until you are very comfortable saying that, okay, I have a success rate of 99%. So only in 1% of the time or in 1% of the images do I do a wrong detection or a mistake. So this process of training and inferencing keeps going on and on till you reduce the number of false positives and false negatives. And that is a very iterative process. And it is, again, this is not, these weights you don't calculate on paper and then enter and then the system is fine-tuned. There are again algorithmic techniques to do this calculation and fine-tuning so that it converges to the best results. So the training will be done in almost like a supercomputer or a big server or a networking platform, because there are a lot of computations done. The output of that is the neural network weight that can be deployed into any system or into any hardware. So like in the Tesla case, whatever values that are incorporated in the processing unit would have been an outcome of a system which was independently and on a larger scale doing all the computations for you. This makes sense? Any questions? I think it's if this is not clear, I can explain a little more in detail. Okay. So this is again another example of a single layer of a neural network. If an image like a NX in white against a black background is given, and we are looking at 3 different term filters. So the term filter, like I said, is the pattern that you are watching out for. So if these 3 patterns are what you are looking for, is a leading, a lagging diagonal, or an X. When you look at this pattern and scan it over this array of pixels, which are 9 by 9, you can see where the values are correlated. For example, 3 successive ones in a diagonal is appearing in all these places. So wherever it sees a high correlation, it gets a very high positive value. Similarly, in this, which is looking for an X, that matches very well at the center. Similarly for the lagging diagonal. So very simply, when you run these 3 term filters over this array, the first step that does the computation of this value against this and summing it, that is convolution. Whatever is correlated, you keep it. Whatever is of low value or negative value, you can say that there is no correlation. It is not very useful data. I can just make it 0. It saves the computation in the next frame. And the last one is polling. So every time you do a 9 by 9 array and keep doing it, the size cannot remain the same because we need to extract features and become smaller and smaller so that we can handle this complexity over multiple layers. So that is called polling. So what you can do is a 3 by 3 array after the first step. you can make it 2 by 2. In the next, it becomes 1 by 1. So as you progressively reduce the size of that frame, but continue to enhance the features that you correlate, it becomes a manageable problem for the computation. So these 3 steps that you do, convolution, rectification, and polling, is what forms one layer of computation. Like that, in each layer, when you do this repeatedly over and over, you will end up extracting the objects of interest as long as you have trained the network in the right way. So the training itself is in an automated way. There is an algorithm for it, and it works on what is called as the loss function or the optimization function. So the loss function or the optimization function is very simply saying what is that I want. So I want a set of weights, and I have a certain picture with the expected results. Now, what is the weights that will give me the correct answer? Go find this out. And what is my loss function? The example is, for example, if you want to go buy a TV, your optimization or what you will look for is the TV with the highest pixel density, the richest contrast, and the lowest price. So these will be the metrics or the cost function for you to go and purchase a TV. Same way, in this neural network, you will say that these criteria, including the false positive and false negative, for a set of images with their expected response, is what I want to optimize. And in optimization, again, there is something, a technique called backpropagation, that is just telling you that if I have 4 inputs, which of these inputs has the most sensitivity, or which of this, if I change, I get the largest change in my output. So I will use that value to retune until such a point that the sensitivity of that parameter reduces and something else increases. Since the idea is to reduce or get to a very low value, you can keep playing with these parameters based on the sensitivity analysis till such a point that you end up with the lowest loss or the lowest computed value, at which point you can say the optimization is done. So these are, I mean, it's a little beyond the talk to go into this details, but what is called a gradient descent, like you're saying, there is a bowl, and how do I get to the lowest point in the bowl, which is my lowest loss function or the most optimized point. That steps to go into the most optimum value through this technique called backpropagation, which tells you for my output to change, which of the inputs has the highest sensitivity. If you keep doing this over multiple iterations, that will allow you to set the weights, and this is the most efficient way in which you can converge to the optimum. So a lot of work and a lot of papers on this, both gradient descent and backpropagation. A very simple example here, very standard, whatever, I think this is about 16 or something layers. And when you do this convolution through these 16 layers, an image of a car comes up with a very high. The thing is, it doesn't say 100% it's a car. This is something very interesting in neural networks, because a truck would also have some matching features to a car, maybe an aeroplane, a horse, which is also surprising, but you will get a probability distribution saying that it's 95% a car, maybe 3% a truck, 2% or 1% an aeroplane, ship, or a horse. So you will never get 100% sure that this is a car, but whatever optimization you do, when I give a car picture and train this network, I will say that my answer has to be 90% or more, and all the other classifications that I have should be less than 10%. Or you can say I want a confidence of 95%, and all the others put together is only 5%. So that also becomes a constraint to your neural network training. Like that, for each image, you can put this criteria. Sometimes if you're not able to optimize, then you have to relax this criteria. And like you're saying, each layer here, the details are probably not in the slide, but if you look closely, is looking for a certain feature or a certain line or curve in the object or the image pixel, like a face or an object or a vehicle. You extract feature for feature. Some of these layers could have complex features which to a normal eye doesn't make sense, but this is how the progression happens across a CNN. And there are already a lot of jokes on CNNs because the kind of time it takes to train, you just have to wait for it to come up with the result. So until then, it is all that heuristic, the gradient descent and back propagation algorithm, which is easily weeks of effort. And the other big issue is that, yes, I give some data, I get some set of weights, I get a result. But if the result is wrong, there is no way for us to go and find out where in this entire layers or in the entire set of weights, things went wrong. So that heuristic or the diagnostic capability is missing. So all you can do is then start with a new set of data, start generating these weights again, and do the training, follow it with your exam paper, which is the inferencing. Keep iterating till you get that sufficient confidence. So this is a simple visualization of how the CNN network works. I think the link is there in the slides that I've sent. In the interest of time, I will skip this. Do look at this video. It's very interesting rendering of how the CNN over multiple layers tries to recognize and correlate to one of the alphabets. So while the neural network or the structure with the set of weights and the computation is one aspect, the industry or even the academic part of it, a lot of work has happened in the different neural networks. So Google has one, Facebook has another. They have done in a way that these computations are most efficient in terms of power, in terms of the hardware complexity, and the success with which they detect a certain set of objects. So that part of it is well understood. That's why there is a lot of hardware platforms for you to go and try. A lot of software libraries, Python, extensively there is TensorFlow, whatever it is. The options are enormous in terms of both hardware and software to go start deploying these machine learning or deep learning structures for various different applications. It could be as simple as a automated attendance system. You don't have to swipe your card. As you walk in, you could have a facial recognition, and then it automatically enters in the system that this person has entered the office. There's a lot, because of the hardware and software libraries and structures available, opens up for a lot of interesting application. So this is one aspect. The other thing I probably would have to emphasize here is that it is also as good as your training data. Unless you have varied training data, without any bias. That is another key thing that you have to underline. If you keep sampling the same set of people for their faces or the same set of roads for the environment conditions, that is a certain bias. Have you done it in a way that you have created enough of these scenarios that an autonomous vehicle will see when deployed in the real world? That is the quality metric of the training data. So people have invested in getting training data so that when they build the neural networks that we saw in the previous section, you can compare how efficient one neural network implementation is against another. So it's like having a standardized question paper. Yes, this is the data we collected. There is this benchmark called KITI. So it tells you that in this, it's a collaboration between Toyota and Karlsruhe Institute in Germany. They have collected city, urban, rural, different light conditions, traffic densities, pedestrians, all those things, marked, unmarked roads, a lot of varied conditions. Over 5 or 10 minutes of data is available. And in each of this frame, what they have done is manually mark the different objects that are existing. Against this, when you do a neural network, have you identified all the objects that were done with the human annotator? If you have done it, then your neural network is very efficient. Again, the metric is the number of false positives and false negatives. Because this data is available and it becomes a common framework, it is like saying a standardized exam paper, right? Otherwise, one person can write one exam, say I got 90%. But if the question paper is different from the other, there is no common comparison between the two. Is 90% could be bad than another person who's getting 80% because the test was difficult. So you can think of the training data as a standardized exam paper with the standardized questions, which are the annotated data, against which your neural network has to perform to a certain expectation. So this is one of the earliest. There have been other developments too. There is this company called Aptiv, and they have created this data set called New Scenes. You can look it up in YouTube. Very interesting. 20-second videos. And in this video, what they have collected is both in Singapore and in Boston. So there is both a left and right hand drive. Different weather conditions, different light conditions in an urban setting, in a main junction. And if you look at the video, it's very interesting. They will put these boxes for you to say, and they are color-coded boxes to say if it is a vehicle or a pedestrian or a traffic light. And that 20-second data is then for you to build your neural network. Very rich data, very varied data. So look this up, it's very interesting. And today, even Google has it. The Google Waymo open data set is there for people to build their own perception algorithm implementations using neural networks. So look this up. The link is there in the slides. So between the neural network implementation, again for which there is standardized hardware and software, and the training data, again multiple people who have made this and made it available for you to go and build your systems. Together, they help you to serve the, the object detection and classification that you want to do. So very simply, the idea here is that on a pedestrian or in whatever urban settings, you are able to do what is called a semantic segmentation. That means you have different colors for the different objects, and it is like a full contour of a person, a car, or a traffic sign or even a light, the road, everything. The problem with this semantic segmentation is that it is computationally very heavy. If you have a lot of players in the road or in the scene and it's changing in a very dynamic manner, it is a lot of computation effort to exactly get the complete contours for all the objects in the scene. So the idea then is that we have what is called a bounding box technique. That is a three-dimensional, what do you want to call it, as a polyhedron. So all you have to do is in a frame by frame, if you have done your object correctly, which is a car, a pedestrian, a cyclist, or traffic light, you put this bounding box, which is a polyhedron structure, and in a frame by frame basis, you only have to update the edges of that contour. Yes, it is slightly inefficient because you can say that the contour of the car is much smaller than the bounding box you put, but then that margin that you lose simplifies in terms of the computation that you have to do. So that's a trade-off that most people do. That's why in many of these videos you will see that they will put a bounding box to identify and track objects which are recognized. This is another nice example. This is from Tesla, the concept called, so all we have done when we saw the neural networks in the training data is supervised learning. What happens is once you have trained and deployed this in real life, once in a while you come to these exceptional situations. For example, here there is a car with a bicycle mounted on the back. This car, the Tesla car following this one, sees it as a car and a cycle. So it does recognize two objects because that was what it was trained for. But in reality, this is one composite object, which is a cycle mounted on a frame or a rack behind the car. So this becomes a new object to classify and train. And they do it in a nice way. Once you get this, you go and ask the cars in the fleet or the system to look for this pattern and collect all the data where you see a cycle mounted on a rear of a car. Now this becomes a new training data for you to again train through your entire network. So you will collect again maybe 100,000 such pictures in different conditions, different illumination, so that variation does not affect the detection process. Retrain your network and then put it back, like how you get an over-the-air update for your cell phone. You get an over-the-air update for the car, in this case Tesla, and then with this new trained weights, you start deploying and collecting data. When you feel that this has done correctly to the required confidence level, then you say that this can be the normal mode of operation. Until then, it's a shadow mode. So it's a working behind the scenes to collect data and process it. And when you have enough confidence, you move over this software update to the normal mode for deployment. I think it's a very neat way, a nice way to keep continuously learning and improving your detection capabilities. And they call this as a fleet learning. So this is like our combined studies. Each of us pick one chapter, learn and teach others. So this is in a very cooperative way, learn from one and share it with the rest of the system. So how does this entire path planning itself work? So the first step in that is to know the contour of this. So if you're going to go from A to B, okay, I have my GPS maps. I know what are the roads and turns I have to take to reach the destination B. Sometimes this is not sufficient because for autonomous cars, the lane itself you need to have a detail to the extent of the lane. So that's what Google has done. Google Waymo, what they have done is in the city of Phoenix, they have run their cars to go and analyze every turn, every junction, every even intersection, and map it to a very high detail using GPS. They might not even rely on GPS. They will rely on the high definition maps in their car to get exactly how you want to go from A to B. This is a static mapping because the roads, infrastructures are largely fixed. Once you know how to go from A to B, maybe in the least time or the most economic way or in the best comfort, these are the layers of optimization that you can add. And this is where the personality of the car comes in. The next is for you to dynamically analyze in the path that you are going, who are the different players. That is the usual suspects, the traffic lights, the cars, the the state or the condition of the traffic light. Is it red? Is it green? Pedestrian, cyclist, everything. Once you know that and you have created these bounding box for the things that you have recognized, you know that based on the traffic light and the available space, what is the next action I have to do in terms of motion planning. And when I do the necessary action, I immediately collect the data. This is whatever your GPS, IMU, wheel sensors, steering angle sensors, everything. And then you can correct it because maybe the weather condition is different. Maybe there is a headwind. Maybe the road is more slippery or it's harder than you thought. There is a more resistance. So that continuous feedback has to come so that you can do immediate corrections to your maneuvering capability. So these 4 steps that you do in terms of the static planning, in terms of the dynamic players, in terms of planning the free path, and then having the local feedback control is what gives you that good autonomous maneuvering capability. I think this is what I was talking about in the previous slide also. Once you know this is the path you have to traverse, you have something called a checkerboard. So for example, this is your autonomous car here, and these are the different cars and trucks in either the opposing lanes or in the lane that you are in has been recognized. In the next few frames, you know how much at what velocity this car is going. So you potentially update where in the next few frames this object can potentially be. Like that you do for each of these players, and then you will get a certain set of boxes or squares which are filled. Then whatever squares that are still empty is what is your free space. So that are potential places in which you can maneuver. So if you think this car is going to brake and in the next few frames you don't have the necessary clearance, you will come up to the decision that it is time to brake and slow down. Or if you think this car is already going at a speed constantly slower than mine, and I have a lane whereby I can switch and overtake, that is also a decision that comes out of this pre-space estimation. The last one probably I will explain here and then stop for questions is something called imitation learning. So this is what I was talking about earlier when I said human-machine interaction. Sometimes when the driver is driving, and for example, if you come to a 4-way intersection and you have negotiated this turn, the interesting thing is while you are doing this, the machine or the computing resource has been observing you, observing in the sense it is still collecting data from the camera. It is still collecting data from the steering angle and your inertial measurement unit. So it pretty much knows from the camera how you moved, and from the steering angle sensor and IMU, what are the actions you did to do that move. So this itself becomes the training data. If you are a good driver and you have done this maneuvering to a certain perfection, just from the data that it collected visually and by action, it can learn to do this in an autonomous manner. So if you collect this information from multiple drivers who have maneuvered that very well, this becomes the data for it to train and specifically look at, for example, how do I make a left turn in a four-way intersection, or how do I exit from a freeway into a suburban road. Very interesting ways, and this concept is called imitation learning, in the sense that you looked at a driver and then you learned from him or her and then used it to do the same maneuvering when you are in the autonomous mode. So a lot of interesting work is happening in this field of neural networks and how it can be trained and deployed to do multiple maneuvers in certain restricted areas or in well-managed roads. So, I mean, today there is again nothing like an off-road capability for autonomous vehicles. It might come over time. Today, they rely on the infrastructure in terms of well-marked roads or on the training data to know that you are in a very controlled environment and use that training to run your autonomous navigation. So this is just the, I would say, the tip of the iceberg. And there are more and more challenges as you go tomorrow. There is always the issue of poor light, weather or rain conditions, unmarked roads, very difficult terrains, or in very dense urban situations, each of which will need unique ways to solve and be able to operate. A lot of it you see today in freeways or in highways where there is no pedestrian traffic. It is very easy to do this autonomous navigation, self-driving cars. But or if it is in your home or in a suburban locality and you want to do an automated park assist or a car, summon your car, it works well there. So there are still a lot of challenges on the technology side to address all this. Not only technology, there are also legal issues, whether you want to, when a human and an autonomous car, human driven and an autonomous car coexist, what are the rules by which you would play? What if it's an accident? Who do you blame? Do you blame an autonomous car if it is the owner or the OEM who made it or the person who wrote the software? So a lot of such legal hurdles are there. We need to create that regulatory framework to operate. Security is an aspect. We saw one example where it was very easy to fool a camera because of a way that object was drawn on road. So like that, each of these sensors can be very easily fooled to go do something which is not the normal. So how do you improve that performance of the sensors? Also, when these cars get connected through any network, it is easy for anybody to hack into the network, hack into your car, get control of any of the CAN, try to do some strange maneuvering. So that security is also an important criteria. And then the last thing is the social one. Irrespective of autonomous cars, different cultures have different ways in which you drive a car. Maybe in the Scandinavian country, see a pedestrian crossing, or if you see the lights turning yellow and red, you would like to stop and wait. In some other cultures, you would like to as well put your feet on the pedal and then jump that transition. So different cultures have different ways in which they drive. How does that characteristic come into an autonomous car? There's also a lot of work there. It's called swarm intelligence. You can look it up. The swarm intelligence says that if I have a set of questions for a set of society of people or a group of people, what would they tend to answer? So if I have 5 or 6 options, what is the option that the group by itself will converge to? So that kind of reflects the culture or the societal aspects of not one individual, but the combined set of people. And that is something you can translate into another neural network and deploy into that autonomous car, which reflects the society. So very interesting ways. I'm just giving an example here. But that we are at the end of this introduction talk. And I quote Newton here, says, if I have seen further than others, it is by standing upon the shoulders of giants. So we make the technology, we create, we solve problems, we create value, and that becomes the platform for the next set of people or the next generation to build upon and improve upon. And that's the way we can solve and address the problems and create a better society. These are my details. Would be interesting to talk to anybody on autonomous navigation. Feel free to reach me with your questions or inputs and feedback. Yeah, thank you. And any questions, just let me know.
Mr. Naren, actually, this is Ramdas again. So
yeah.
For the medical and the finance domains, there are regulatory bodies. Yes. In the sense that they lay down the standards and the products have to undergo the certification. And of course, even for automotive also, we have certain things like functional safety, which is offered by TÜV and others. But for this autonomous version of the flavor of the work, is there any kind of regulatory standards that evolved recently, or anybody is talking about it, or anybody is contemplating, or ready for release that kind of?
Correct. Today, I think one is the coexistence that I was talking about. We are not going to go fully manual to fully autonomous overnight. So when you are going to take these baby steps, or when to some extent you are going to coexist between a human driven car and a machine driven car, what are the rules by which you will play, right? That is one aspect. The security aspect is also another, be it again a human driven car or an autonomous car. How do you ensure of the safety or the security? Safety is there, functional safety, redundancy, all that is there today. It will, the sensors that come in, the computations that you come in, if you see that hardware, there is duplicated processing just to ensure that even if one CPU or GPU fails, the other one can keep doing the thing without any disruption. So that's functional safety, redundancy. In terms of security, they already have a standard now to go and address the security aspect of these cars as they get more and more electronics and more connected. The third is the coexistence part of it, that largely falls on the government to bring in the regulatory aspects. Either do you want to do it only in certain regions? For example, in the US, they have enabled Google Waymo to operate in Phoenix area under certain restricted conditions. Singapore is also trying to do that. Do we want to allow them in certain localities, or do we want to give them a dedicated lane? So a lot of that today is falling purely on the government to bring in the necessary legal framework, and as a result, the certification also.
Okay, so as an expert in this, I mean, somebody is working on this technology. How do you see that the career map can be? Basically, now a lot of people are doing a lot of work, especially the biggies are doing a lot of work, and a lot of many startups are coming in, and a lot of chip designs are happening.
Yeah.
A lot of software is being built, and how do you see that landscape basically is going to evolve?
See, yeah, that's why I said overnight, I don't think we will ever go to a fully autonomous. That might be the end goal or a long-term goal. The immediate thing is, see, again, one size does not fit all. Different countries will approach this autonomous or even assisted navigation to solve their own problems or improve their own uh, economics, or even improve their own society. I mean, one example is in Netherlands, they are talking of this concept called truck platooning. The idea is that you can have a set of whatever 20 trucks, one follows the other. The first lead truck is probably human driven, and all the trucks that follow are locked to the one behind, or sorry, locked to the truck in front. So you don't need drivers in any of the other 19 trucks. The first one, the driver drives it entirely, and all the guys following come with the necessary sensors to maintain the clearance. So that helps reduce the amount of human effort that goes in shipping products. Their ports are very famous, and from there they go all over Europe to be distributed. And since they have a set of well-connected roadways, this will help them do it very efficiently from one warehouse to another. So I'm just giving you an example of how the autonomous navigation is being deployed in real life for a certain economic benefit. Similarly, sorry. So similarly, we have to see what is it that the autonomous or assisted navigation can help us. In the Indian context, I would say safety, right? We might not have that level of interconnected and well-marked roads, but then with all these sensors and with all this computing, can we improve the safety on the roads? This might be as simple as in the highways, being able to have these early warning detections for anybody who is trying to cross the road or any stray objects on the road, or even look at your own driver. For example, the truck drivers are heavily stressed, or they work very long hours because of the pressure in going and delivering on time. Sometimes the early morning hours, they just doze off and they don't realize. So can we use these technologies? For example, look inward, look at the driver, is he paying attention? If not, can you do some corrective or safety maneuvers so that either you reduce the speed of the vehicle or you move to a safe harbor so that you don't create this accident, thereby improve the safety performance. So those would be the initial baby steps. And from then, as that technology matures and you can deploy in more and more systems, you can add more and more layers of autonomous or assisted navigation. Then you can bring in cruise control. You can bring in lane departure or lane keeping assistance. All these things, as you add layers, will make it more and more autonomous. And that's the progression you will probably see.
Okay, thank you.
Thank you.
Hello, sir. My name is Vishnu, and my question is about sensor fusing, actually. Yeah, so like you said, I want to talk about the reliability aspects of the GPUs because, like you said, information from 2, 3 other or more, 3 or 4,
Yes.
sensors are being it's been fed into the GPU. So what about the reliability issues of this thing in the long run?
I mean, reliability in the sense of the
What if it
data.
takes- No, not about the data. It's about the hardware itself, the GPU itself.
See, that's why I don't know. Just I'm just going to that picture. I'm just opening this slide. 1 second. So that so this board or the computing unit you see here, Vishnu.
Yes, sir. Yes.
If you look in finer detail, there are 2 massive chips here. Each of this is a dedicated processing unit, and they can pretty much independently do the same computation. What by having this redundancy is make sure each one validates the other. So only when both of these computing units give you the same result will the processing move forward. Otherwise, you junk the data and you'll take the next frame of data to process. So that is the kind of redundancy built into the system to avoid any data processing or computation errors. This is like saying, okay, an Airbus twin engine, it has 2 engines for the best efficiency. Okay, but even if one engine fails, right, with just the other, it can still fly the entire way. It might not be efficient, but it can do it with the necessary safety. Okay. The analogy is the same here. So 2 dedicated units to compute so that you have a very good reliable way to judge your data. But even if one fails, then you will not do any complicated maneuvers, but you will be able to still run the system to such an extent that you can maybe do a safe harbor, pull over the car, and then report that my system, one of the units is not working, right? So that is the kind of, I mean, not only the hardware computation, but the higher level of decision making that will make these systems very robust. So an engine fails in the aircraft, the pilot can make a decision whether can I go the entire way with this engine, or do I need to go to the nearest airport and land? Yeah. So the same kind of decision making has to be incorporated. You can even rely on connected cars then. If the car reports that my system is failing, a remote pilot can take over the car and drive it also to the destination. Very interesting ways then to solve this issue.
True. Thank you, sir. Thanks a lot.
Yeah. Any other questions? Yeah, it not, yeah.
Yeah, thanks for nice discussion. One question I have is like, say today when we are stuck in traffic jam, like in accident kind of situation, which is which may not be available upfront, and when we hit in such traffic jams, so typically as humans we are equipped enough to how to react those situations. So my question is like how the autonomous vehicle behaves in such situations, and is anybody studying in such situations?
See, that's why I said one is to think ahead and say, can we even avoid the traffic situation at all? Right? the congestion. That is where just that autonomous car, not only just the autonomous car, but autonomous plus connected cars, as you are exchanging information in real time. So you know what is your destination, you know at what speed you're doing, and whether there is up ahead there is an accident or a restricted lane or a congestion. You can start planning up ahead. Is there an alternate route? Not only for one car, for a set of cars itself. The connected cars and a common distribution or a common control unit can tell cars, command the cars to go take these alternate routes and start redistributing so that you don't see the pileup. I'm just giving a very simple example here. One is, so the idea is, can we even by planning out how these cars go, in what path or in what road and at what speed, can we even plan it in a way that we will avoid these congestions? So it might not be the fastest way, but it can be the most efficient way in terms of whatever fuel economy or something.
Sir, actually, my question is slightly different here. So I mean to say, like, when that information is not available ahead, I mean to say, like, say suppose you are traveling on a motorway. Typically in motorways, whenever there is a city, then only you can take some turn and you can enter, and that's how the happens. But on free highways, it is not suppose if there is a accident happens, say 5 minutes before, so you didn't get that chance to take the alternate route. So typically it goes and stops there. So as a human beings, and second thing is like I'm talking a situation where you have the mixed pool of autonomous vehicles and human driven cars is there. So as a human beings, like, okay, we need to wait until the as per the program, like we'll wait for some time and we'll see, like, we can take a different lane and we can pass on it when there is a chance is there. But in autonomous vehicle, how does it behave in such a situation?
Correct. So at the simplest level, it will understand that there is an obstruction, and then it will just stay there till such point that the obstruction has gone away or it sees an alternate lane to operate. So that then really becomes a factor of the training data. Is your car, autonomous car, trained to handle this scenario whereby I can switch over to another lane and continue my path to the destination? Otherwise, forever it is just stuck at that place. Then the only way out of that is to say that to raise an emergency or something, and for some remote pilot to come and take it out of that situation, put it back in the road, and then it can continue, which is not a very efficient way then. So like that, there will always come scenarios for which you have never trained. So then that's why I'm saying these are very simple today, the machine learning that you do. For those exceptional situations, can you leverage what you have learned, and then can you add your own capabilities to go and find a solution? That is like thinking on the fly. That is where a lot of work, interesting work, will happen in this realm of artificial intelligence. I'm saying it from the context of the car. You can apply it to your real life situations also. So for example, Alexa can do a very good job of your voice recognition and query back whatever you ask. Your Google phone is very good in remembering faces, identifying the contours of your face, etc. But let's say, can you put two and together and have a system which can recognize the person, his voice, then his human or his emotional characteristics, and accordingly fine tune your response, right? That is where humans have evolved very well, and where all this, what we talk of machine learning systems, are limited in their scope today.
Thank you, sir.
Yeah, that aggregated intelligence of many other things, small things, is where the real challenge is. How good can you mimic human intelligence? Any other questions? Yeah. If not, you can always reach out to me. We can have a discussion offline. And I hope the last 2 days talk has been an interesting eye-opener for all of you in this field of autonomous navigation technology. It is indeed a very interesting area for me personally, because of the interplay of so many systems, mechanical, like I said, mechanical, electrical, electronics, the computer science aspects. So people with interdisciplinary skills will find this very interesting to go solve those challenges and start creating some interesting solutions in the Indian context too. Thank you. Shekhar, anything you want to add?
No, that's good, Narayan. Thanks a lot. And I think this has given a good overview. Obviously, there are a lot of things to be implemented even after taking all the readily available hardware and software. So that's just a pointer to everyone. We are also going to start a kind of a boot camp course that will go on from late August all the way to December, wherein actual hands-on with the systems will be done, and the participants will be working with a bench top or a toy vehicle with the autonomous elements, and cover all the aspects, the electrification, the autonomous, and so on, kind of taking what you have been through into a reality, right? So that's a course that is going to start from 21st of August and go on till December. Weekend classes over the weekend, and a lot of homework to be done. It's basically given as a total assignment-based construction of the course. So that's all I have. If you need any more details, you can always contact our training team. And thanks again, Narayan, for the time today.
Yes, Shekhar. Thank you. And if you find some interesting problems to solve in the Indian context.
Yes. Okay. Thank you, everyone. Thanks for the time.
Good evening and bye.